Let's look at volumes by disks for rotations about axes. And I'm going to draw out what I mean by this, but what we're going to be doing is we're going to be taking our two-dimensional drawing, so our XY axis. We're going to be taking the curve, and we found the area under that curve. So for instance, if I have, just say a simple curve like so. We've found the area under that curve. We've said that if we put a shape on top of that curve, we can find the volume of that using cross sections. That was the last video. What I'm going to be doing now is taking this curve and rotating it around an axis. So for instance, let's say we want to rotate around the x-axis. It's rotating like so. Let me just draw it as a whole line. And so we're going to be rotating it. And so what we do, we're spinning it. We're forming this kind of not quite spherical region, kind of a spherical region that's coming to more of a point on the end. And so as we're rotating these figures, we are forming a volume. We're taking a two-dimensional figure, rotating it to create this third dimension, this three-dimensional figure. Now we're going to have several ways to calculate these volumes when we do these rotations. The method we're going to look at in this video is by disks, and these are great for a picture like this when there is no middle removed, when we don't have anything taken out of the inside. But think about something like maybe a bead. So if we had that larger outer radius and then we had some inner curve as well, and we rotate both of these shapes, we're looking at this region in here. And so, like I said, picture a bead. Think about a bead, because again, this thing is really curved the whole way around. This thing's a curve the whole way around. And so we have this almost spherical region, but with the center cut out. We have that drilled out. And so for something like this, we're going to have to use another method. We're going to use either washers or cylindrical shells, and we will look at those in the follow-up videos. Now, as I've stated before, I'm not a great drawer, so this does challenge me to draw these in 3 dimensions, but you're going to see them. I'm going to do pretty basic pictures like this, just to get ideas down on paper, so I can try and create some sort of visualization of what I'm dealing with. I will be sending out other links that do a better job of really illustrating this 3D nature, just so we can get a better picture in our head. But when you guys are drawing your own pictures, I don't expect you to be artists. I am not. But draw a picture. Start with a picture, because that is the best way to get information down on paper. So again, we're going to be working 3 different methods for these rotations about axes. We're going to be finding volumes by disks, washers, and shells. We're going to start with these disks. And so let's come back to this first picture, because this is the one that we're going to concentrate on for disks, that when we don't have that center removed. So if we think about how to find the volume of this thing, well, let's think about it again in terms of those cross sections that we were dealing with in the last video. So I'm taking that little red slice, and when I take that slice, I get that green curve in there, that green circle really. I'm getting a circle. That's what I get. If I rotate these shapes about the x-axis, each little cut is a circle. And so if we think about how to find the area of a circle, it's pi r squared. And then if we think about how to find a volume, this is what we were doing in the last video when we were taking our two-dimensional pictures, our curves, and we're placing a shape on top of it. We're just multiplying by the height element. And so to get to that volume, we're going to take our area and multiply by the height. Now, those areas are changing. That's what's going to give us the integral. That's why we need to set up an integral, because it's not just a consistent circle. We can see that this circle is obviously much smaller than this circle, and then they get smaller again. So we're going to have to do some integration here, because the radii of the circles are changing. And so this is where this first formula is coming from. Notice we have the integral from a to b of the area of the circle at a given position x times the height, which that depends on how far we've come along the x. So dx would give us the height. And then when we think about that area, what we said the area was, it's pi r squared. So we see pi and then radius squared. Now why am I using a big R there? Because again, that R is not consistent. We tend to use that little r if we have just say a circle of radius 5. But here all of our circles are changing, and so we have to think of that radius as a function itself, and that radius is a function of the position it is along the x-axis. And so we can think about finding that radius, the radius would be, let me use yet another color, the radius would be the distance from the, well, it's not going to switch over, but from my point right here to the curve. And so the radius is purely the function's value at that x value. We're just going to use that function value to give us the radius. So let's take a look at an example. We'll put it all together in an example so we can really see what's going on. Let's find the volume of the region between y equals x squared for x between 0 and 3 and the x-axis generated by rotating the region about the x-axis. Okay, so the first thing I'm going to do is I'm going to start with picture. So x squared, we know what that looks like. Then we have, we're told we're looking at a region between that x squared and the x-axis between 0 and 3. So we are looking at this green shaded figure, and of course we're rotating that. And so we are getting, a kind of an increasing region, almost kind of like a cone, but a cone where the sides are kind of swooping out a little bit faster. Parabolic cone where the sides are swooping out a little bit faster. It's not just a straight on the edges. So I should also point out we are rotating about the x-axis, which is why I drew my circles around the x-axis. So now let's think about all of our elements. If we take those cross sections, we see they are circles. And so we can find the area of those circles, pi r squared. And what is our r? Well, the r is the distance from the x-axis to the curve itself, which is just the function. It's x squared. But it's going to be x squared squared because we have pi r squared. We're clearly going to integrate from 0 to 3 because those were our boundaries given. And so let's set it up in the formula. So we have the integration from 0 to 3, pi x squared squared, and then the height. Well, the height is dependent on how far along the x-axis we are, so that would be the dx. First thing I'm going to do is factor out the pi, or pull out the pi, not really factor, but pull out the pi, and then we have x squared squared, which is x to the 4th, dx. Now I can calculate this antiderivative. It would be pi over 5, x to the 5th, and we're calculating that between 0 and 3. And so we'd have pi over 5, 3 to the 5th, minus, of course, 0 to the 5th. And 3 to the 5th is 243 over 5 pi. And so that would be our answer. It is a volume, so the units would be cubed if we knew what the units were, but we don't know what our units are. So there is our volume. That was pretty straightforward, I think, as long as we understand how those cross sections work from last week, or from the last video rather. All we're doing is we're using the same cross sections just on this different three-dimensional shape that we're creating by spinning the curve around the x-axis. But why are we spinning around the x-axis? Why couldn't we instead spin about the y-axis? So this is just the same definition from before, or the same formula from before, but I want to now look at what happens if I spin it about the y-axis. So if we're spinning a curve about the y-axis, right, whatever our curve might be, and now we're going to be spinning it this direction, well, we're going to have to make some adjustments. Because our radius is now a function of x on y, it's going to have to be in terms of a slightly different radius. We're going to have to change that radius around. The radius isn't going to be a function on x, it's going to be that function on y. we're going to have to redefine the function. And what that means is everything needs to be in terms of y, because if we think about our height, that is dependent on how far up the y-axis we are. So our height is now actually dy. And what that means too is that we're going to have to change our limits of integration to be in terms of y. And so I'm going to just call them c to d. Again, these are just the placeholders until we actually calculate what they are. Switch that over to a d. And so from wherever we start, my picture here, I've started at 0 and then I've gone up to whatever d I actually want to calculate. Those are just the limits of integration along the y-axis now. So let me change this one over to, I was messing with that second one. But it's going to be the same exact formula, but we're doing everything in terms of the y now instead of the x, because we're rotating around that y-axis. Otherwise, it will be the same exact idea. So let's just jump right into an example. Let us see here. Find the volume generated by revolving the region enclosed by x is equal to y to the 3/2 power, x is equal to 0, and y is equal to 2 about the y-axis. So the first thing let's do, let's draw it out. So x equals y to the 3/2 power. It might be easier to think about what that would look like in terms of the x. So that would be x squared divided by, or x to the 2/3 power. So some sort of cubic root, but happening maybe a little bit faster. And then we have the other boundaries of x is equal to 0. That would be down here. And y is equal to, let's try that again. That would not be down there. That's x is equal to 0. That should be the y-axis. And then y is equal to 2 would be over here. So we have this region right here that we are spinning about our y-axis. So we have clearly our function is going to give us that radius. If we think about the radius point from here to here, that is given to us by the function y to the 3/2 power. If we think about where we're integrating to and from, we're clearly starting at 0, and we're integrating to this point right here, which was y is equal to 2. I put the 2 on the complete wrong axis. The y equals 2 would be this line up here. I had that drawn correctly. And then we're clearly integrating from 0 to 2, or we're finding the volume from 0 to 2. We're going to have our pi, our r, y to the 3/2 needs to be squared dy, and I'll call it my volume, so I'll put my v out front. We can simplify that a little bit. One thing I can pull out the pi, and then if I take y to 3/2 and square, it's y to the 3rd dy. So we'll get pi over 4 y to the 4th, and we're going to integrate that from 0 to 2. And so we'll have pi over 4, 2 to the 4th minus 0 to the 4th, 2 to the 4th is 16, and then 16 divided by 4 is 4. And so that would be our volume, 4 pi units cubed. So pretty straightforward when we don't have that center removed. When we're not removing anything from the center, we only have the one curve to deal with. We do just need to make sure that is in terms of the right variable. If we're rotating it around the y, it better be in terms of y. If we're rotating about the x, it better be in terms of x, and everything better be in terms of x. So we need the dx, we need the x function here, we need the limits from a to b to be in terms of x, or from c to d in terms of y. So we need to make sure we're consistent. That's going to be a common theme throughout these volume problems. We need to make sure that we're consistent. But it is pretty straightforward because we don't have anything we have to remove from that center. We are going to go into the other methods in the next two videos. We're going to look at the washer method first, and then we will look at the shells method. The washer method, I think we're probably going to be pretty comfortable with as it is. If I'm taking something out of the center, use my red here, if I'm taking another curve out of my center, I can clearly see that I'm just going to do essentially the same thing. I'm just thinking about this in terms of those same discs, and I can subtract it from the larger. Or I could do it a little more concisely by thinking about this larger radius and subtracting the inner radius. And so we'll go more into depth in the next video. I just wanted to give you a little taste of what is to come.